What we're going to demonstrate now is some pulse measurements. Pulse measurements are very common in digital systems, data communication systems, because pulses are what define the characteristics of those systems. In order to understand these systems, we often want to look at things like pulse amplitudes, absolute levels of these pulses with respect to ground, how wide are the pulses, what kind of rise times do we have, what kind of duty factors do we have. So we'll show you those measurements on the 2465. We have here a pulse which is representative of the sort of pulses that we'll find in digital systems. And we have on the 2445 and 2465 a new set of controls, delta volts, delta time, and cursor controls, which we'll be using to measure this pulse with its various parameters. First, let's measure the amplitude of the pulse. And we'll do that by pressing the delta volts button and positioning our cursors to coincide with the top and bottom of the pulse. And having done that, we see that the amplitude of the pulse is 2.95 volts. Now, very often, of even greater significance is the location of each of these levels with respect to ground. So let's make that measurement. To do that, we change the input coupling of the channel that's displaying the signal to ground, and we move the reference cursor to overlap the trace that we have in the ground position. We reconnect the signal, and now we see that the positive level of the signal is plus 1.86 volts. And now to see the bottom or negative level, minus 1.09 volts. Other measurements are equally easy to make. To measure the period of the signal, we simply align each of the cursors with an identical feature of the signal, and we can read as delta time. The period is 15.4 microseconds. Another measurement is width. Simply moving the cursors to each side of the pulse gives us the pulse width of 2.3 microseconds. Now, we could use these numbers that we have just derived and calculate the duty factor, or an easier way to do that is to rotate the variable seconds per division control until we have at least, or rather exactly, 5 divisions covered by one cycle of the signal. Now, 5 divisions are defined as 100% for ratio measurements. So, if we superimpose the cursors now on the edges of the pulse, we have a ratio measurement made directly. Now, we can get a little bit better accuracy on this duty factor measurement. In this case, because our pulse is a little bit less than 1 division in width, and obviously we can't set those cursors as well with such a small signal as we could if it were larger. So let's turn on our horizontal magnifier and position it so that we can see both edges. Now reposition the cursors to correspond to the magnified pulse. And now we have, in reality, 14.8% duty factor, a little bit different number than we got earlier, and we can be more confident of that number. Another measurement that is often neglected because it is normally rather difficult to make is rise time. To make this measurement, we simply speed up the sweep until the rise time occupies a significant amount of horizontal displacement. Well, it's a little bit too fast. At 1 nanosecond per division. First of all, we should set the amplitude so it's exactly 5 divisions so that we can use the rise time marks of the graticule. Now, our delta time measurement allows us to measure rise time by simply placing each cursor at the 10% point and the 90% point as defined by the rise time marks of the graticule. And we have a 4.64 nanosecond rise time. While we've set the vertical variable to obtain our 5 division reference, we can also make ratio measurements in the vertical direction. And one way to use that is to measure these aberrations. As you can see, we have about 3.7% amplitude of ringing. Another important pulse property to measure, which we'll illustrate with this length of cable in a different pulse generator setup, is propagation delay. We'll connect this cable into the channel 2 path. We'll display channel 2. Superimpose these vertically around the center of the screen. And let's expand it so we can see that interval easily. And let's put some numbers on that interval by aligning the delta time cursors with the points where the transitions cross the center line. And we can see that this length of cable then is 1.34 nanoseconds long. One important feature of the 2445 and 2465 that adds to our confidence in making these measurements is a matching feature for the channel 2 delay. We'll set that up by taking out our cable and reestablishing a matched signal path for channel 1 and channel 2. In setting our seconds per division control at the highest speed, then pulling it out, instead of getting the B sweep display, we get a channel 2 delay message. And it instructs us to rotate the delta control. And this provides plus and minus 500 picoseconds of adjustment of the channel 2 delay time. And of course, we'll end up precisely matched between channel 1 and channel 2. Then when we push the button or the second per division knob back in, that setting is stored in a non-volatile memory. And every time we make a propagation delay measurement in the future, that information will be used. Some of the measurements that are important in communications and control systems are frequency, phase, and modulation. We're going to demonstrate some of those measurements using the delta volts and delta time cursors and the cursor controls that are found in the 2465 and 2445. We'll start with just an ordinary sine wave here, which we can expand for a reasonable display. By pushing both delta volts and delta time together, we obtain a 1 over delta time display. And now we can align our cursors with 0 crossings of the signal, exactly 1 cycle apart. And the time interval that's defined by those cursors is now interpreted as frequency. And we see here a frequency 5.97 megahertz. Let's change our signal generator to a higher frequency and repeat the measurement. Again, setting the cursors to cross the signal at the same place the signal crosses a graticule line gives us a reading of 244 megahertz. Let's raise the frequency again. And repeat the measurement. Again, sitting at 0 crossings. (517 megahertz). This is just a little beyond the guaranteed trigger range of the oscilloscope. Another measurement is phase. Now, to demonstrate that, we will apply our signal to channel 1 and channel 2 simultaneously. And we're going to have to lower the frequency slightly to get within the range of easy phase measurements and adjust our volts per division. Now, one of the requirements for measuring phase is that one cycle of the signal occupy at exactly 5 divisions of the horizontal display. So to make that happen, we're going to have to adjust the variable. But the entire display moves, so let's start out by measuring the period of the signal. We'll go to delta time for that measurement. 2.66 nanoseconds. Now we'll divide that by 5. And that gives us 532 picoseconds. Now we will turn the variable seconds per division control until we have a reading of 532 picoseconds in the second per division readout. Now we should have one cycle every 5 divisions of the horizontal. The next step is to verify which of these is our channel 1 reference signal, and then to carefully center both channels so that our 0 crossings are truly in the center of the signals. Then let's select our phase mode by pushing both delta V and delta T together. And then align each cursor with the respective signal. The reference cursor with the channel 1 0 crossing and the delta cursor with the channel 2 0 crossing. And we see that channel 2 occurs 188 degrees behind channel 1, or we have a phase lag for this frequency of 188 degrees in this short length of cable. Another frequency measurement is a swept frequency measurement. Here we have a swept frequency sine wave, where the frequency is determined by a ramp which we've displayed on channel 3. We're using channel 3 as the trigger source, and with auto level and the level control set fully counterclockwise, we're triggering very near the origin of that ramp. So we are displaying the swept waveform. Let's take a look at the frequency at each end of this swept burst. First of all, at this end, obviously we can get better resolution by turning on the magnifier, so let's do that. And let's measure the frequency of this last cycle. .1 kilohertz. And at the other end, let's measure from the falling edge of the first cycle to the falling edge of the second cycle. 10.9 kilohertz. What we have here is a sine wave that's frequency modulated by the audio on this videotape. Again, if we adjust our display so that one cycle of the carrier is 5 divisions horizontally, we can make a ratio measurement. Now, the ratio measurement in this case is going to be the peak-to-peak frequency modulation in terms of percentage of carrier frequency. Now, of course, this is a live signal, and it varies, so we will make an estimate of the highest level, which appears to be about 18%. If we want to measure amplitude modulation of an RF carrier, such as we have here, we will start by adjusting with the variable volts per division the displayed amplitude to be exactly 5 divisions, which corresponds to 100%. Then we connect our modulating signal, turn on our delta volts cursors, which give us a ratio reading because the variable volts per division is out of detent. Align the cursors with the peaks of the modulation and read the modulation percentage, 52.7%. Slew rate measurements are fairly common in communication and especially control systems. They're normally made by making a voltage interval measurement, a time interval measurement, and taking the ratio of those measurements. The 2445 and 2465 have a method of making that measurement that requires no calculation. In order to make this measurement, we first would like to expand the display for good resolution. We'll turn on the horizontal magnifier, and we'll also increase the vertical sensitivity. Now, since we've set the vertical at 200 millivolts per division, 1 volt is now 5 divisions in the vertical direction. Now we'll turn on the 1 over delta time function, getting the cursors, and we'll position them at the points where the waveform crosses graticule lines that are 5 divisions apart. And we have a number, 1.61 megahertz. Now, we can interpret that, since instead of displaying one cycle between the cursors, as we normally do for 1 over delta time, we are displaying 1 volt. We can interpret that as 1.61 megavolts per second. We're more comfortable with the concept of 1.61 volts per microsecond for most applications, however. We're now going to discuss time measurements. With the 2445 and 2465, there are 4 techniques. Each technique has unique applications and unique accuracies, which we'll discuss. To illustrate these various techniques, we have a fairly complex display of 4 channels and 15 states. First of all, let's make a very simple measurement using delta time cursors. Let's measure the period of the signal on channel 4, which is at the bottom of the screen. Very simply, we have 15.78 microseconds. Now, for a better view of that, let's first of all remove the other channels. And now let's turn on our delayed sweep by pulling out the second per division knob, and you'll see that the cursors are replaced by intensified zones on the sweep. Now, to observe that time interval with better resolution, we'll turn the knob. Let's reposition this upwards and back up the intensified zones just a bit until we see those edges on the B sweep. Now, by speeding up the B sweep, we expand our view of this time interval, of these transitions, and so we can set the delta time controls more accurately. And now we see that our time interval is really closer to 15.81 microseconds. Now, in fact, largely because of the setability of the cursors, the accuracy using delta time cursors will be 1.25% or better. However, using the delayed sweep method that we're showing now, the accuracy will be 0.55% or better. Another use of the delayed sweep measurements is for looking at details. Let's return to our original display. And let's examine the setup time between the data, which is on channel 1, and the clock, which is on channel 3. And let's select for measurement this final pulse here. As you can see, that's a very small interval, not very easy to measure with the cursors. So instead of depending on the cursors, let's go ahead and use the B-sweep. Again, we pull the knob out, rotate it for better resolution. Now, we no longer need channel 4 to establish our frame of reference, so let's turn that one off. Here's our data, and here's the corresponding clock. If we set those so they cross the same graticule, we see the setup time is 0.35 microsecond. Now in this particular case, we can obtain slightly better accuracy of the measurement by using the graticule directly on the B-sweep rather than the delta time measurement. This is because the time interval is less than 1/2 of 1 division on the A-sweep. To make the measurement that way, we simply turn off delta time, then adjust the delay until we can see the data event and the clock event on the same screen. If we superimpose these signals vertically, we should do that on the center graticule line, and count the divisions, multiply by 50 nanoseconds, we will have a slightly more accurate measurement. However, the convenience of the delta time measurement probably means that is the preferred method. Another reason for making measurements from the graticule rather than using a delta time, delayed sweep, or delta time cursors could be a single event that can only be observed in a photograph where there's no time to set up cursors or delayed sweep. One more method that can be used to turn this interval that we're now observing on the graticule into a number directly is to use the second per division variable. And here we will speed up by 1 speed, set the beginning of the interval, which is the data pulse, at the left edge of the graticule, then set the clock edge to the other side of the graticule, and now we can make this measurement by looking at our second per division calibration, which is 36 nanoseconds per division. Now, since this is 10 divisions, that interval represents 360 nanoseconds, a slightly different number from the one that we obtained using the delayed sweep. Now, the accuracy of this measurement, as long as the interval that we are measuring is at least, or rather exactly 10 divisions, will be 3.3%. Okay, let's summarize these 4 measurement techniques. First, cursors give us 1.25% accuracy. They're the most often used method because they're the easiest. And incidentally, they do give us the best available accuracy for time intervals less than 10 nanoseconds on the 2465 or less than 20 nanoseconds on the 2445. The second technique uses the delayed sweep. The delayed sweep gives us the best accuracy for time intervals greater than 10 nanoseconds or 20 nanoseconds for the 2445. That accuracy is 0.55%. The delayed sweep also gives us the best view of detailed features of the signal. The third time measurement technique makes use of the oscilloscope graticule directly. This gives us the most accurate measure of expanded details when the detail that's expanded is less than 1/2 division on the delaying sweep. The accuracy we can obtain from the graticule will be 2.2% as long as the interval is at least 4 divisions long. The graticule is, of course, our only way of measuring isolated events that can be viewed only on a photograph. The fourth method makes use of the variable second per division control and the graticule. Again, this is a method for viewing or measuring expanded details of a complex signal or isolated bursts. This method can give us 3.3% accuracy. With any of the 4 measurement techniques, the best available accuracy will be obtained by expanding the display as much as possible. This minimizes errors due to visual resolution and CRT nonlinearities. The triggering capabilities of the 2465 and 2445 are very broad, very versatile. To demonstrate those, we're going to exercise the controls here in the trigger block: mode, source, coupling selections, the level control, and the hold-off control. Let's begin with the mode control, which we'll set to auto level. Now, the function of the auto level mode is to limit the range of the level control to fit inside the peak-to-peak range of the signal, so that no matter where we set the level control, we will be triggered on the signal. Also, the entire range of the signal will be covered between the fully left horizontal position of the level control and the fully right horizontal position of the level control. Ordinarily, the level control is not needed in auto level. We have a hands-off trigger where the scope sets the level automatically. The scope will set the trigger level automatically under any one of 3 conditions. The first condition we'll show is the loss of triggering due to a change in the triggering signal. Now, if the signal changes again, notice that the trigger level remains constant. And this brings about the second means of changing, that is, of reacquiring the trigger level range. As we turn the trigger level control, we'll see that we come to the end of its range just below the positive peak of the signal the last time it reacquired the trigger. If we want to trigger at a higher level, the natural thing to do is to continue turning the trigger level control, and when we reach the end of the control, the trigger level range is reacquired. It is reset to the level of the new signal. Now, the third means of reacquiring the triggering signal, that is the range of the trigger level by auto level, is to push up the mode switch while the auto level mode is active. When this happens, we lose trigger momentarily and the trigger level is reset. When the trigger level is reacquired and the range of the trigger level control is reset by the auto level mode, the trigger level will be automatically set to one of three positions. If the level control is fully counterclockwise, the level selected will automatically be near the negative peak. That is, just slightly positive of the negative peak. If the control is fully clockwise, it will be set very near the positive peak. And if the control is somewhere between, when the trigger level range is reacquired, the level will be very near the 50% point, that is midway between the positive and negative peaks. Now the auto level trigger mode will function for any signal with a 50 hertz or higher rep rate over the entire range of the second per division control. But at the slower sweeps, the low frequency limit is extended even lower. The next mode to look at is the auto mode. In this mode, the sweep free runs in the absence of trigger, just as in auto level. The difference is that the range of the level control is no longer confined to the signal. In fact, it extends over plus and minus 18 divisions when the source is channel 1 or channel 2. And it extends over a range of plus and minus 9 divisions when the source is channel 3 or channel 4. The advantage of the auto mode is that we can set a precise trigger level, for example, the TTL threshold, and under all signal conditions, that level will be maintained, and yet, if the signal disappears or goes to a logic low or a logic high, we still have a bright baseline that tells us where that DC level is. This mode operates for all signal rep rates down to 20 hertz, except at the slower sweeps where that's extended to even lower frequencies. The normal mode is identical to the auto mode, except that when the signal is not sufficient for a trigger, the CRT is blank. No sweep occurs. To demonstrate the single sequence mode, let's first slow down the sweep so we can easily see what's happening. Now, selecting single sequence, we can see that we get one occurrence of the sweep and also one occurrence of the readout display after that. A single sequence is different from single sweep in that if we select more than one trace to be displayed, single sequence causes one occurrence of each of those selected traces and then the readout. As long as that sequence is not complete, the ready light is illuminated to indicate that, and the triggered light, of course, indicates each of the triggers as they occur. The 2465 and 2445 provide very versatile trigger source selection. The trigger source selection includes all four of the vertical inputs. The selections are independent between the A sweep and the B sweep, and they are also independent of the vertical, except of course in vertical source, where the trigger source selection follows the vertical display selection. Conspicuous by its absence is external trigger and also trigger view. These functions are really superseded by this simplified set of functions that also has greater versatility. Now, while the vertical source is selected, we have really two modes of operation. When the mode is either auto or normal, and also including single sequence, the vertical source produces a composite trigger. That is, each of the selected channels in turn provides a trigger, provided the vertical mode selection includes the alternate switching mode rather than chop. If we select chop instead of alternate, the source selection is automatically the lowest numbered of the displayed channels, so that the scope does not trigger on the switching waveform, rather it triggers on a valid signal waveform. Also, if the trigger mode is auto level, the lowest numbered channel is selected as the trigger source regardless of the condition of the chop alternate switch. So as we select and deselect channels, we do change the trigger source, but the trigger source selected is always the lowest numbered of those that are displayed. For the A sweep, we also have a power line trigger source. Let's now take a look at the various coupling selections. DC coupling is the most often used selection. In this instrument, the trigger signal is independent of vertical positioning, so this is now feasible. The advantage of DC coupling is that it provides the most stable trigger with the largest variety of signals, especially digital signals with varying duty factors. DC coupling also gives us a trigger level readout. Now we have displayed on screen here a signal with superimposed noise. Now the noise has sufficient amplitude to trigger the sweep, and so we are seeing a trigger on each slope of the lower frequency signal. To eliminate that, we simply switch to noise reject triggering, and that low amplitude noise is rejected. Noise reject is an amplitude discriminating mode, which also preserves the trigger level readout, except in this display we are generating this mixed signal by using the add vertical mode. When the interfering signal increases in amplitude, it may not be possible to reject it based on amplitude discrimination. In many cases, the frequency difference between the desired signal and the interfering signal is such that HF reject coupling will show us the display that we're interested in. The cutoff frequency for HF reject is 50 kilohertz. It is a DC coupled mode. If the signal of interest is the higher frequency signal rather than the low frequency signal, we can use LF reject coupling. And now speed up the sweep, and we see the higher frequency signal, and the low frequency signal is simply a position modulation of the higher frequency signal. The primary application of AC coupling is for signals that are riding on varying levels of DC offset, the AC coupling mode blocks the DC component of the signal and maintains a trigger. In contrast, DC coupling applies this varying DC offset to the trigger circuit as well, and when the signal is offset far enough, the trigger is lost. The A and B triggers share the same controls, however they are independent. When we operate the B sweep by pulling, unlocking the second per division knob, we then have the ability to select the B triggers by pushing the AB trig button, and we have one of two choices for the B trigger mode, either run after delay or triggerable after delay. As you can see, if we select triggerable after delay, we have the status of the source, coupling, and slope selections for the B trigger. In addition, we have independent control of the B trigger level, and the trigger level that was previously established for the A trigger is maintained even though we're changing this control. Now when we lock the knobs together, the display of the A trigger status is automatically selected. Now there's another case in which we pull the second per division knob. If the B mode was trigger after delay, the LEDs immediately show us what the B trigger status is so that we are alerted to the requirement for B triggers. Of course, we can change the mode to run after delay if we like, and if we prefer to operate on the A trigger even though the B sweep is displayed, we simply push the AB trig button. Finally, even though the knobs may be locked, we can take a look at, and in fact change, if we so desire, the B trigger by holding the AB trig button depressed while we're making those selections. But unless the B sweep is displayed, those have no effect. Likewise, while the knobs are unlocked and the B trigger after delay mode is selected, we can take a look at the A trigger and modify it without affecting the B trigger. And then when we release the button, the controls are immediately reverted to the B trigger. The final trigger control is the hold-off control. As you see this display, it is triggered, but the sequence of pulses is not well related to the sweep. By turning the hold-off control, we can find a place where we have a more stable display of that pulse sequence. Now the reason this works is that the hold-off allows us to adjust the timing cycle for the sweep. The time cycle for the sweep comprises the time that the sweep takes to move the beam across the CRT, a short time that elapses while the beam is retraced back to the starting point, and then an additional time which is adjusted by the hold-off control, which in this case forces the trigger to wait until the beginning of the next cycle of this irregular sequence of pulses. One advantage of the 2465 and 2445 hold-off control is that it provides a hold-off time which is at least equal to the sweep duration time for all sweep speeds faster than 100 milliseconds per division. One more convenient feature of the trigger can be illustrated with this DC offset control on the signal generator. You can see that as we move this DC voltage to various levels, that we have a readout in the trigger level readout that shows us that DC voltage. Now this is convenient for tracing power supply distribution in a complicated system. The accuracy is about 5%. The 2465 and 2445 have several features for assuring the accuracy of measurements. Most of these features center on the use of the calibrator. The calibrator waveform is well defined for shape, amplitude, and period. First, let's take a look at the use of the calibrator for probe compensation. This is a very conventional technique in which we simply adjust with a small screwdriver the probe response for a good square wave. It is critical for this setting that the second per division control be set at 1 millisecond as indicated on the front panel. The second test that we can make is amplitude calibration, volts per division calibration. By aligning the waveform at 100 millivolts per division with the graticule, we can see the error in the vertical calibration. And if we look very carefully, we can see that the vertical gain is just slightly less than ideal. Another test that we want to make is delta volts calibration. So we'll align the cursors with this waveform, and as we can see, the amplitude is 398 millivolts as indicated by the cursors, well within the 2% specification. Now, the use of the calibrator for timing depends on the fact that the calibrator period is controlled by the seconds per division switch. So at every seconds per division setting where it's possible, the calibrator frequency is adjusted so that we have 5 cycles across the entire screen. So let's just start at one end. It's a bit hard to see at this speed. At 100 milliseconds per division, we have 5 cycles per screen. Now, as we continue to the very fastest speeds, we begin to see the rise time of the calibrator, and because of the vertical delay, we'll need to reposition the waveform. In fact, we're now at the point where we are at the highest frequency available from the calibrator. So as we continue to higher speeds, we have to use the waveform in a little bit different manner. Here we know the period is 200 nanoseconds, and so we look at the center 8 divisions, which is 400 nanoseconds at 50 nanoseconds per division. At the next speed, we'll need to change our trigger level and horizontal position so that we can align the rising edge with each edge, the outside edges of the graticule, to verify 20 nanoseconds per division. Now, as we continue, we have less than 1 cycle. So we're going to have to use a different technique. And this it does not give us the same accuracy, but it will give us some assurance that the timing is correct. If we observe the transition time at 20 nanoseconds per division and continue to observe that at the higher speeds, we can see that indeed the sweep does increase its speed by about a factor of 2 for each of those fastest sweeps. The calibrator is also adequate to verify the magnifier. We turn on the times 10 magnifier at a moderate speed so that we're not seeing the transition time of the signal. 1/2 cycle of the calibrator should be exactly 10 divisions. And if we look carefully, we can see that it is. If there's any doubt about the symmetry of the waveform, which there shouldn't be, we can look at both half cycles and observe that either half cycle gives us very nearly 10 divisions. For making time interval measurements between two different signals on two different channels, we need to know that the probes and the vertical channels of the scope are well matched for propagation delay. The 2465, 2445 provide a feature that allows us to do that very precisely. First of all, we connect both channels to a fast pulse, superimpose the signals vertically, go to the fastest speed with the magnifier on, then we pull out the second per division knob. Now, ordinarily this would give us a delayed sweep display, but since we're at the fastest speed and there is no faster delayed sweep, we have the channel 2 delay message, which tells us to turn the delta control. And when we do that, we can see that we're displacing the channel 2 waveform by as much as plus and minus 500 picoseconds. Now, if we align those so that they are at the same time, then push the knob in the future we'll be able to depend on accurate time interval measurements. Now, for the best accuracy in trigger level readout and to minimize the shifting of the trace as we rotate the volts per division knobs, there is a function which has previously been adjusted with a small screwdriver, which in the 2465 and 2445 is automatic. This is the vertical DC balance, in which the instrument automatically cycles through all the volts per divisions and makes an ideal DC balance adjustment. The P6131 standard accessory probe for the 2465 and 2445 presents a 10 megohm and 11 picofarad load to the signal under test. It's available, or it can be configured, in 4 different grounding configurations, as we see here. We have a coaxial configuration, which is simply a bare metal ground exterior and a signal input at the tip. We have a Z ground, which can be pivoted to adjust the spacing between a ground point and the signal point. A hook tip, which can attach to a axial lead device or a DIP pin. And finally, a rather long alligator clip ground. Each of these configurations obviously has application advantages, but unfortunately, as we increase the length of the ground, the fidelity of the waveform is deteriorated. We'll now demonstrate the effect of each of these grounding techniques on a real signal. Let's begin with the coaxial configuration. Simply touching the signal to the center conductor of this BNC connector and grounding the shell, we see a fairly good response. Now, as we speed up the sweep, we can see a better view of that. And at the fastest speed, we can measure the rise time, 1.1 nanoseconds. Now let's take a look at the Z ground. See right away a large overshoot appears, and we see the rise time has increased slightly to 1.2 nanoseconds. Next, let's look at the ground wire with the hook. We see our overshoot plus some additional ringing, and the rise time now is 1.7 nanoseconds. Finally, let's look at the longest ground wire with the alligator clip. The ringing is accentuated further, and the rise time becomes 2.09 nanoseconds. Now, the moral of this story is that for quick signal tracing, anything will do as a ground, but for careful signal analysis, you should always use the shortest possible ground. And remember to take the structure of the circuit under test into consideration as well, and place the ground connection as close to the signal source as possible.